Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSC, working at Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the various definitions and terminology in graph theory. So the very first thing is that, so what is a graph? So graph is nothing but a ordered pair consisting of set of vertices and then set of edges. And these vertices and edges are going to be represented in the form of the set. So what we call it as a vertex set, and the edge set is this one. So here, if I'm going to consider this graph, so what are the vertices in the graph? So that may be W, X, Y, and then Z. So these are the vertices, and these things are represented in the vertex set. And if I'm going to consider the edges here, so what are the edges in this one? So E1, E2, E3, E4, E5, E6, and E7. So these are the edges, and these edges are going to be represented in edge set B. So the graph is nothing but the collection of vertices and then edges. So if I want to define a graph properly here, so graph is nothing but a non-linear data structure, so which consists of vertices, nodes connected by edges, where the edges may be directed or indirect. So the graphs are powerful and versatile data structures that is going to allow to represent the real life relationship between different types of nodes. And there are two types of graphs, what we call it as direct and indirect graph. And if I'm going to consider this the part of the graph here, that I can able to have vertices and then edges here. So a graph is nothing but a linear data structure which is consisting of vertices and then edges. So the other synonyms what I can able to call these vertices as the nodes, and the edges can be represented as arms. So the graphs are powerful versatile data structure which is going to be show the relationship between different types of the data. So normally the graphs is going to be divided into two parts, what we call as vertices and then edges here. Suppose how can I able to say this edges are going to be adjacent? So the vertices I and S have to be adjacent if I'm going to connect with the edge with an edge here. So what are graph representations? So the graph representation is nothing but which is going to be in the form of adjacency list and then adjacency matrix here. So the graph representation is said to be situation, so which is going to be represented in two ways. So first one is that adjacency matrix and adjacency list. That means whatever the graph we are going to have, so that the should be represented in the form of matrix here. So matrix is nothing but V1, V2, V3, and V4. I'm able to consider this, and if I'm going to have an edge from V1 and V2, I can able to represent that should be 1 and V1 to V3, and there is no edge from V1 to V4, so that's why it should be 0. And similarly, there is no edge self loop for V1, so it should be 0. Similarly, if I'm going to consider V2, so V1 and then V4, that should be 1, so the remaining should be 0. And similarly, if I'm going to consider V3 here, so V3 is V1 and then V4, that should be 0. And from V4, it should be V2 and V3. So like this, I can able to represent the adjacency matrix here. And similarly, if I'm going to represent adjacency list, so if I'm going to consider here, so what are the edges that are connected for V1 is V2 and then V3. So like this, I can able to represent. This should be representation of adjacency list. So what are the various pros and cons of this adjacency matrix? So this adjacency matrix is a two-dimensional array. So where I can able to represent in the form of rows and columns. And so between the pair of vertices, the cost of edge is going to be stored. And this is going to be show which vertices are adjacent to one another. And for the indirect graph, so half of the graph is repeated information. So this is the disadvantage of this. We should able to said to be space inefficient, and the memory use of this adjacency matrix is the equal estimate of n square, where n should be the number of vertices. So these are the various pros and cons of this adjacency matrix here. So between the pair of what are the various disadvantages, advantages of this adjacency matrix is that, so since the between the pair of vertices the cost is going to be stored, so it should be that the vertices are said to be adjacent to one another. And for a directed graph, half of the graph is repeated information, so that it is going to be have and one of the disadvantage. So if you look at this, so the same information is also going to be repeated here also, and for this one also same. So this is the one of the disadvantage of this adjacency matrix. And what are the advantages of this adjacency matrix is that, so it should be easy to understand and implement and convenient to work, and you should be able to remove edges with a time complexity of estimate of 1. So the queries like whether an edge from vertex U to vertex V are efficient and require the time complexity of 1. So if I'm going to say, if I'm going to have a graph like this, and this graph is going to return the form of rows and columns, and these are the where the adjacency matrix is going to be filled with the values of zeros and ones, and if I'm going to have an edge in between the two vertices, that should be 1 here. Otherwise, if there is no edge in between this, I can able to represent 0 here. So the advantages of the adjacency matrix is that, so it should be easy to understood and easy convenient to work, and should be able to remove the edge, and we should also the queries like whether there is an edge from vertex V to vertex V should be an efficient, and time required complexity should be 1. So what are the disadvantages of using this adjacency matrix is that, so it should be able to consume more space, and even if the graph is dispersed, and it should also consume the same space, and adding the vertex should be equal estimate of V square. And if the number of nodes in the graph may change, the matrix representation should be too inflexible also. So what are the pros and cons of the adjacency list here? So in this representation, each vertex of the graph contains a list of adjacent vertices, and these advantages of using this adjacency list is as follows. So the addition of vertex and connecting the new vertices with the existing one should be easier, and we should also have the space complexity, and it allows us to store some graph in more compact form, and then can able to get the list of adjacent vertices in big estimate of 1 time, which should be a big benefit of some algorithms. So here in this representation, so our vertex of the graph should be adjacent, and the advantages of using this adjacency list should be that it should be easier one, and should have some space complexity as well, and it should also allow us to store in more compact form. And when it comes to disadvantages of this adjacency list, the queries like whether there is an edge from vertex V to vertex E not efficient, and should also require the time complexity of estimate of V, and it does not allow us to make an efficient implementation, and if the dynamic change of vertices is going to be required. So this disadvantage of adjacency list is that, so the queries like whether there is an edge from vertex V to are not efficient, and should be able to require the big estimate of time complexity, and should not also not allow to take the efficient implementation also. So what are the different types of graphs here? So in this different types of graphs, so we're going to have 3 categories. So first one is the undirected graph, directed graph, and rotated graph. So undirected graph is nothing but all the edges that are undirected, and if the connection is symmetric, in other words, it should be connected, A is connected to B, so and then also B is connected to A. So the undirected graph means that, so if I'm going to have the vertices like this, the edge is going to be how undirected, there is no directions in between them, so that's why it should be an undirected graph. And similarly, if I'm going to maintain the directions in between the vertices, then I can able to say they should be this directed graph. If I'm not going to maintain the vertices, then it should be undirected graph. So weighted graph means that, so here in the edges, I'm going to assign some weights in between them. So I can able to say this should be the weighted undirected graph. Whereas if I'm going to maintain the arrows, then I can able to say this should be weighted directed graph. So these are the different types of graphs here, where I can able to say three tabs. So that should be undirected, means that all the edges should be undirected, and directed means all the edges should be directed, and weighted graph is the graph where each edge is going to be associated with numerical value. So what can able to call it as a weight. So undirected graph. So undirected graph is nothing but a pair of vertices representing by an edge which should be in an order. So every tree becomes a also a graph, but every graph may not become a tree. So undirected graph is said to be connected if there is a path between every pair of vertices in the graph. So undirected graph means that a graph is said to be undirected or connected if there exists a path between every pair of vertices in the graph. And directed graph means that, so the edge is going to be represented with an arrow here, and there should be a directed path in the diagram, which should be nothing but the sequence of distinct vertices such that there is an edge from vertex V vertex in sequence to next here. So this is the directed graph where the edges are going to make the directions in between them. And weighted graph. So weighted graph is the graph where the edge is going to have associated numerical value, what we can able to call this as weight. And weighted graph may be directed and indirected. And the weight of the edge is often referred to as cost of the edge. Example. So if I'm going to have like this, so each and edge, the weights are going to be assigned for edges of this vertices in between them. So that's why this one, or what we call it as a weighted graph here. And next one is that, so what are the different types of graph traversal techniques? So the graph traversal techniques means, first of all, how to know what should be graph traversal. So graph traversal means that visiting all the nodes of the graph, and if you want to visit every vertex and every edge exactly once in the same well-defined order, then there should be two different primary traversal algorithms. So first one is that breadth first search, and next one is the depth first search. So these are the two basic traversal techniques here. So breadth first search and depth first search. So in breadth first search, so we have to visit all the vertices of the graph in level by level, not by level by. Suppose in BFS, so first we have to visit this one, and all the nodes which are present in next level should be visited. And similarly, if I'm going to visit all the vertices in next level, then it should be this BFS order. So DFS means that, so in DFS first we have to visit this node, and next we have to visit this node, and each and every time we have to visit only one node at a time, and we have to be backtracking, have to perform, and then we have to visit the next level nodes, this one, and then you have to perform backtracking and have to visit the next level, and next one is this, and next level is this, and again you have to perform backtracking and come down to the next level. Now node one you have to visit this one and this one, and then you have to come back and then again you have to perform this. So like this, we have to visit all the BFS traversing and BFS traversing event. So if you look at this algorithm, so the steps should be same here. So first we have to visit the node, and then have to put the n children nodes in the list, and then for each child we have to be search the child of that. So for this, if I'm going to perform the DFS, then I have to make use of stack data structure, And similarly, if I want to make use of BFO, I have to make use of queue data structure. Okay. So visit the node and then identify the children of the nodes, and then we have to place all the childs in the appropriate data structure, whether it may be a stack and then queue. So if I'm going to use the stack, then I can able to get BFS order, and if I'm going to use a queue, I can able to get BFS order. So BFS, that should be bread for search. So visit to all the children before the first grandchild, and then visiting order should be first visit the vertex and visit all the neighbors, and then visit all the neighbors of this neighbor. This is the path you can able to follow for implementing BFS. And BFS is the best when I'm going to use to find the best spot in the given graph. And you can also need the flag or somewhere to prevent the infinite loop. That should be a weakness here. And this is the BFS algorithm. So create the queue and then mark the B as listed and put the queue. So while queue is not empty, remove the head of the queue and then mark it into and leave of the lines. And we are going to see some of the basic terminologies of these loops and multiple edges. So a loop is nothing but an edge whose endpoints are should to be equal. So this should be the loop, and multiple edges means the edges is going to have some pair of endpoints. And okay, so an edge whose endpoints are equal, that should be the loop, and edges is nothing but the edges going to have same pair of endpoints. And simple graph, a graph which is not going to have no loops and multiple edges, that should be the simple graph. And if it is not simple, then I can able to treat this should be the multiple edges and the loop. And if it is simple graph, it should not contain any self loops and multiple edges. So a simple graph is the graph which is going to have no loops and then parallel edges. Okay, so the simple graph does not have any kind of loops and then parallel. Then I can able to say it should be the simple graph. And adjacent. So how can I able to say that the two vertices are said to be adjacent? So the two vertices A and B are said to be adjacent if there is an edge that is connected between the 2 points. An example here. So A and B are adjacent since there is an edge that is connected between the 2 vertices. If I'm going to consider this A and D here, so there is no edge connected between A and D, then the A and D should not be an adjacent. And what is the difference between finite graph and null graph here? So finite graph is the graph whose vertex set and edge set should be the finite one, and null graph means the graph whose vertex set and edge set should be empty. So a graph whose vertex set and edge set is said to be finite, that should be the finite graph, and the graph whose vertex set and edge should be empty, I can call that should be the null. So what is the difference between connected and disconnected? So connected means there exists at least one path between the 2 vertices, and disconnected means otherwise. So here the H1 and H2 are said to be connected because so each and every vertex is connected by means of edge. So H1 and H2 are said to be connected, and H3 is said to be disconnected because there is no edge is connected between A and B and then E and D. So that's why we should be disconnected. Okay, so how can I able to say the definitions of the term connected and disconnected? So if there is a path of vertex between the 2 vertices, I can able to say that 2 vertices are said to be connected, one otherwise should be disconnected. And next one is a complete graph. So means that a simple graph is which every pair of vertices are said to be adjacent. Then I can able to say that should be the complete graph. So if I'm going to have one vertex, 2 vertices, so in which every pair of vertices are said to be adjacent if the number of vertices is equal to n, and there may be n minus 1 edges. So if I'm going to have like this, so we should do a complete graph. If I'm going to have 2, so there is going to be only one edge that is connected to the 2 points, that edge should be connected one. And here, so if I'm going to consider this vertex, there is an edge from vertex 1, 2, 2 and then 3, and I'm going to consider 2, 3 like this. So similarly, I'm going to consider 4, this should be the complete graph. I'm going to consider 5, so this should be the looking of this complete graph. And complete graph. So where the number of vertices should be 6, and this should be in case of 7, and this should be in case of 8 here. And another definition, so we're going to see is spurs and graph and then dense graph. So what is a spurs graph here? So a graph is said to be spurs if the modulus of E should be equal to modulus of V, and graph is said to be dense means the mod of E should be the mod of V square, which should be the spurs and then dense graph. So what is this directed graph here? So normally the other synonym in directed graph is that, so the edges going to have the directions. That should be the directed graph. And weighted graph means, so whenever I'm going to consider a graph, the weights are going to be represented in the edge. So that's why it should be treated as a weighted graph. And similarly, if I'm going to consider weighted directed and weighted undirected also. And next one is that planar graph. So whenever I'm going to graph in a plane space, then I can able to say that should be the planar graph. And the next one, complement of G. So complement of G means quite opposite of that graph is nothing but the complementary of the graph, simple graph. So if I'm going to consider a simple graph, so the quite opposite of this edges is different. So the vertices should be same, but the edges should be quite opposite. There is an edge here. The complement of that means there should not be any edge in between them. So if I'm going to have the edge here, so I will not have the edge in between them. So this graph what I'm able to call it as a complementary. So those and all will be the basics of terminologies of this module 1, that should be graph C. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.